ionic compounds. So the big thing with ionic compounds is when you're naming them, when you're looking at an ionic compound, trying to decide whether it's ionic or not, ionic always include a metal and a non-metal, for grade 9 anyway. There is one exception. That one exception is boron. Boron is a non-metal, but it will act like a metal for ionic compounds for grade 9. Okay? The first ion is named according to the periodic table, and it tends to be the metal. And again, that one exception of boron. So sodium would just be sodium. Magnesium is just magnesium. So that's how we name it. The second ion is the non-metal, and we change the ending to IDE. So chlorine becomes chloride. Fluorine becomes fluoride. Oxygen becomes oxide. Excellent. So the first one there, NaCl is sodium chloride. The second one here, magnesium and fluorine becomes magnesium fluoride. Perfect. So that was if you were given the formula and you had to write the name out. So you're given the formula, MgF2 or whatever it was, you have to write out the name. Now, if you're given the name and you are then have to write out the formula, this is the process that you would use. So the process, you write the symbols. There's 3 steps. Write the symbols for each ion present. Obtain their charges is step number 2. And then the third step is write the formula using the crisscross method. So we're going to do an example of that right now. So the first one's lithium bromide. What's the symbol for lithium? What's the symbol for bromine? Br. There. That is the first step done. Second step is obtain their charges. What is the charge for on a lithium ion? +1. What is the charge on a bromine atom? Ion? -1. Lithium is trying to get rid of an electron, so it's getting rid of a negative, so it's going to end up with a positive charge. Bromine is trying to go and find an electron, so it's going to take on more negatives, so it's going to end up with a negative charge. And this will be the same for all ionic compounds. The first one, the metal, are always trying to get rid of electrons, so they're always going to be positive. The second one, the non-metal, is always trying to find electrons. It's always going to be negative. All right? So that's step 2 done. Step 3, we crisscross them. Now here's how you crisscross. You take this number on the lithium and you write it down there. And you take this number and you write it down there. So right now they're superscripts. We make them subscripts, but we switch them. And you drop the signs. So there's no plus or minus anymore, because now it's just a number. So if this becomes Li1, Br1. So notice I've dropped the signs. No more positive, no more negative. Okay? Now, scientists, notoriously lazy, they don't have to write something, they won't. So it's agreed upon that you don't need to write the ones. So if ever you see a 1 in a chemical formula, you can actually just leave it out and write LiBr, and then we're done. So we write the symbols for magnesium chloride, Mg and Cl, magnesium and chlorine. We obtain their charges. What's the charge on a magnesium ion? +2. What's the charge on a chlorine atom? Ion? -1. Chlorine needs 1. It's in group 17. Okay? Now we crisscross this. So that one goes there. That one goes there. And we rewrite this as Mg1Cl2. Again, I drop the signs. I don't need the plus or the minus anymore. And I can drop the 1. So I can just rewrite this as MgCl2. So what that's saying is that for every 1 magnesium, we have 1 magnesium here, I need 2 chlorines. Think about the example we did yesterday, where the other day, where we had someone pretending to be magnesium, and they had 2 valence electrons. I think we acted this out, right? So 2 valence electrons. Magnesium had to go and find a chlorine atom. Chlorine took 1 of those electrons. but magnesium still wasn't happy because magnesium still had that extra electron. So magnesium had to go and find another chlorine atom. Gave away one to each chlorine atom. Both chlorines are happy. Magnesium is happy, but it took 2 chlorines for 1 magnesium. So that's what this is all about. These numbers here, it's the ratio that we need to make this compound. We need 1 magnesium, 2 chlorine. What was the third example there? Sodium oxide. Sodium oxide? Sodium. So sodium is Na. Oxide, that's oxygen, so that would be just O. Obtain their charges. So sodium has a charge of +1. Oxygen has a charge of -2. Crisscross it. That goes there. That goes there. And you're left with Na2O. Now, if you're comfortable with this, you can skip right to this step. You don't need to write the ones and then do another one where you show no ones. All right? I just did the first couple of examples with this extra step so that you could see where those ones were going, where those numbers were going. All right? But you don't actually need to do it. You can leave it. You can just skip right to this step here and be done. Okay? Now I want to talk about 2 special cases. Special case number 1 is boron. We've already been talking about boron a lot, so let's do boron sulfide. So boron is B. What's the symbol for sulfur? S. So I didn't go with boron oxide at least, because we wouldn't want to have BO. So boron sulfide. So what's the charge for a boron ion? +3. And the charge for a sulfur ion? -2. Now the reason why this one's a special case is because boron is a non-metal. All right? But it will still form ionic compounds like this. Crisscross it, and you end up with B2S3. And again, that is the only way, for grade 9 anyway, that's the only way that boron and sulfur are going to join up. That's the ratio. You need 2 borons and 3 sulfurs. All right? The last special case I want to talk about is if we get this happening. So let's do beryllium and oxygen. BeO. So beryllium and oxygen. What's the charge on a beryllium ion? +2. What's the charge on a oxygen ion? -2. Crisscross that. And the formula is going to be Be2O2. But let's think about this for a second. How many valence electrons does a single beryllium have? 2. So beryllium's looking to give away 2 valence electrons. How many valence electrons is oxygen looking to get? 2. So if we had 2 atoms here, 1 beryllium and 1 oxygen right at the front, and then we had 2 more, because that's what this is saying. We need 2 berylliums and 2 oxygens, right? So you're going to be beryllium, you're going to be oxygen. You're going to be beryllium, you're going to be oxygen. Let's look at this first group. Okay, beryllium number 1, you have 2 valence electrons. You give them to oxygen number 1. Okay? So actually do that. There's your electrons. Give to oxygen. Okay, oxygen, are you happy? Beryllium, are you happy?
Yes.
Okay, did we need this other beryllium and oxygen to make these 2 happy? No. So they're happy by themselves. Beryllium number 2. Let's pretend you had 2 valence electrons. You give it to oxygen number 2, right? Oxygen number 2, are you happy? Yes. Beryllium number 2, are you happy? Yeah. Did you need these 2 over here to make you happy? No. So again, it's about the ratio to, by which you're going to satisfy those outer electrons. So this these two atoms right here, we're able to do that without those two atoms. So it's about the ratios. So when you have a common factor, you can reduce. So there's a common factor of 2 here. So we can rewrite this formula as BeO. And that's true for all ionic. Only ionic. So if you had boron nitride and you do crisscross, you're going to get B3N3. Can we reduce that? Yeah, it's a common factor, so we can just make that Bn. Okay? In grade 9, the only ones you're going to get will be 2 and 2 and 3 and 3. All right? You won't see any 4 and 2. You won't see any 4 and 4 or anything like that. So it'll be 2 and 2, 3 and 3, and that's it. And you can only do this with ionic compounds. So if there's a metal and a non-metal. If we looked at H2O2, we've talked about that a little bit. What's H2O2? Hydrogen peroxide. Is hydrogen a metal? Is oxygen a metal? So we have 2 non-metals. So this is not an ionic compound. So you can't reduce this. You can't make this HO. All right? You can only do that with ionic compounds, so a metal and a non-metal one. So that was ionic compounds. This is the other type. This is covalent. It's also known as molecular compounds. So if you are given a formula for a molecular or covalent compound, first thing you need to do is be able to identify it. So ionic has a metal and a non-metal. Covalent will have 2 non-metals. So like hydrogen and oxygen, or carbon and oxygen, or any 2 non-metals. And in order to write out the name for this one, you need to use prefixes. So here are the prefixes that you are responsible for knowing. Oh, and that's there. So very important to realize that when you're naming ionic compounds, you don't need to use prefixes because there's only one recipe. There's only one combination. So if you've got sodium chloride, there's only one way for sodium and chlorine to come together for grade 9 science. So we don't use prefixes for those. But for covalent, if you've got, say, carbon and oxygen, we've all heard of carbon dioxide. We've all heard of carbon monoxide. So that's just different ways that carbon and oxygen are coming together. And that, because there's different recipes for the same 2 elements, that's why we need to use the prefixes, so that you know what the recipe is that you're looking at. Because there's a very big difference between carbon dioxide and carbon monoxide. Try these 3 examples here. Okay, so for the first one there, what would be the proper chemical name for CO2? Well, there's 1 carbon, so we would use the prefix mono. So it'd be monocarbon dioxide. However, have you ever heard someone refer to it as monocarbon dioxide? No, and that's because, again, scientists have made a special rule. And that special rule is, if the first element in a covalent compound is single, is all by itself, is a single carbon in this case, then you can drop the prefix mono. But it only applies, again, that rule only applies to the first element and only if it's single. So for the second one there, if you wrote down the name according to the rules, you probably wrote mononitrogen trioxide, but we can drop the mono and just call it nitrogen trioxide. What about the third one there? Tetraphosphorus decaoxide. We have to use the prefix tetra because it's not a single phosphorus. We have to use this prefix tetra, so it's tetraphosphorus decaoxide. All right, so for writing out the formulas, it's a lot easier with covalent because the names have the recipe in them. So in ionic, we had to do crisscross to figure out what the recipe was. For covalent, the names are right there. The recipe's right in there. Nitrogen monoxide. So 1 nitrogen, 1 oxygen, right? So what's the formula? NO. No! What's the formula for the second one? Carbon tetrachloride. Carbon Cl4. Because it's carbon, so singular. Tetra is 4, chloride. Okay, the first one here, nitrogen, so 1 nitrogen, 1 oxygen.